Good morning, ladies and gentlemen, boys and girls, fellow Homo sapiens. Welcome to the wonderful world of today. Thank you for joining. Hope everything's going okay for you. This particular problem hopefully comes from page 147 in the textbook. It should be example problem or problem in the book number 36. This deals again with coefficients of frictions and an angle. So we have to resolve some forces. With that, let's get started. Things I know. Remember, we should always start our problem with the things I know. Well, I know G equals 9.81 meters per second squared. That's the acceleration due to gravity. We should know that already. We know then that the theta, the angle, is 30.0 degrees. We know that there is a net acceleration in the x direction. So the acceleration in the x direction is 1.20 meters per second squared. The mass of the object is unknown. Slightly tricky, but we can deal with that. And what do we want to find? We want to find mu sub k. Okay? Because our mass is unknown, we're going to have to substitute in and solve this algebraically. Again, tell you, I generally always start with a picture. Now I'm going to start with one here. So we have an incline. We know that angle is theta. On that incline, we have some sort of box. Okay, remember, we simplify our pictures in physics. I'm not going to write anything or draw anything really creative. It's basically a box. We know the forces that are acting on that box are, we have a normal force. That again is the surface pressing directly up on the box. And remember, that's always perpendicular to the surface you are on. So in this case, it's pointing up and away. And remember, we have now created our axis to follow along. The positive x-axis will be down the incline. The positive y-axis is perpendicular to the incline. Okay? From there, we also have then a force due to gravity that is acting straight down. And we have a frictional force, a force of kinetic friction that is acting up the incline. How do I know it's acting up the incline? The frictional force is always opposite the direction of motion. If it's going down the incline with an acceleration, frictional force must be acting up the incline. These are the forces we have acting on the system. We have one force, though, that isn't along the axes. We have that the force due to gravity is not acting along the axis. Now remember, force due to gravity is simply mg. Well, as we break that down along the axis, I have a y component that acts straight into, and since those are supposed to be equal and opposite, I better make the other one a little bigger. Sorry about that. And then we have an x component that is acting down the incline. And remember, this is the force due to gravity in the y direction. This is the force due to gravity in the x direction. We are resolving or decomposing or breaking this down into the components that act along the vector, the axes of the problem. Remember, all of these forces are acting on the object, so we could draw them, that parallelogram method I've talked about, we can draw them like this, and it's still the same vectors. So the F component of the gravity is acting down the incline, the Y component of the gravity is going into the incline. That's what we get to know. We also know then that the sum of the forces in the y direction must be equal to the net force in the y direction, which is equal to 0. Why? It is not accelerating vertically. It is not moving off the incline upwards. It is not going into the incline downwards. If there is no acceleration, the force then has to be 0 along that axis. So we have the net force there equal to 0. that equals the normal force minus the y component of gravity. So we know that 0 must equal the normal force minus the y component of gravity. Well, the y component of gravity is simply equal to, then, well, if this is gravity, remember gravity, the force due to gravity is simply mg. If this is the y component, remember, this angle here we've already shown you is the same as that angle there. Therefore, this y component must be mg, its gravity, times the cosine of the angle between the hypotenuse, which is gravity, and that side. So that is the cosine of theta. That is my y component of gravity, the force due to that. So we have then that the normal force must equal mg cosine of theta. For this to be 0, these two values have to have the same magnitude. So, the normal force must be mg cosine theta here. Our incline problems, if we know this angle, we know that angle, so then this is always going to be here. It is going to be mg cosine theta. That means the x component here, which is the opposite side. Remember, when we're doing our trig, the opposite side is going to be the sine function. This x component here must be mg sine of theta. So, right now we know the normal force is this. So I'm going to write it over here. F sub n equals mg cosine of theta. Well then, we also know, or we need to look at the sum of the forces in the x direction. Remember, this is the summation symbol. This is a term for the magnitude of the forces. It's not the vector. The vector would have the arrow across. This is simply the magnitude. Well, what must that equal? Well, it's the net force in the x direction, which is that is equal to the mass of the system times the acceleration in the x direction. It is not 0 in this case because this is accelerating down the incline. Therefore, this must be equal to our forces in the x direction. Well, it's got the kinetic friction force going up the incline, and it's got gravity moving it down the incline. Those two are my forces that are acting here. If I'm accelerating down the incline, this one must be bigger than that. So we have chosen our axes to be positive y up out of the incline, positive x down the incline. So that must be equal to then my net force, which is my mass times my acceleration in the x direction, must be equal to the force due to gravity in the x direction minus the force of kinetic friction. My force of kinetic friction is a simple equation. F sub k equals mu sub k times my normal force. We've already solved for this. I wrote it up over here. Okay, we know what this is. It's mg sine of theta. How do we know that? There's my angle. This vector is mg. This is the opposite side. It must be mg sine of theta. So this must equal mg sine of theta minus mu sub k f sub n. That equals max. But we know the normal force. We can substitute in as mg cosine of theta. And notice what happens. My mass can be canceled out as a factor of all my terms. leaving me then that AX equals G sine of theta minus mu sub k G cosine of theta. Now, I want to isolate this term, which means I need to get it alone. So I'm going to add this value to both sides. So I'm going to get AX plus mu k G cosine of theta equals G sine of theta. Subtract the acceleration. I get mu sub k G cosine of theta equals G sine of theta minus A sub x, the acceleration in the x direction. Okay, kind of running out of space here. Move over. I'm going to divide both sides by G cosine theta. Remember, if there's an equal sign, as long as I do the same thing to both sides, I haven't messed up the math. So I'm going to get that mu sub k must equal G sine of theta minus AX over G cosine of theta. This is a whole quantity on top. So I can't cancel out the G that way. Now we've got everything solved, and I know all of these terms. I was given the acceleration, I know what the angle is, and we know what G is. So mu sub k must equal then 9.81 times the sine of 30, not theta, 30 now, minus 1.20. Again, this is in meters per second squared. This is a unitless number. This is in meters per second squared, and the bottom is in meters per second squared. My units are going to cancel out, which is good. That's what we want. And this is going to be over 9.81 times the cosine of 30. Well, this is simply equal to then 9.81 times the sine of 30. That should be 1/2. So I get, sorry, I've already calculated this. So I should get 4.905, which is basically that divided by 2, minus 1.20 over, well, this, I believe, is the root 3 over 2, which is not a nice number. You've got it on your calculator, but multiplying that through should give me 8.4957 ... more numbers. When I finally solve this, remember, I'm subtracting. Where should I be here? I should have 3 significant digits. There's my third significant digit. Third significant digit. So from the top, I should be good to the 100th place. On the bottom, I should only have 3 significant digits, which is good to the 100th place. So my final answer should have 3 significant digits. When I do that, I should get 0.4361 and some other numbers. Remember, it is now unitless, which leaves me then with 0.436 as my coefficient of kinetic friction. Hopefully that was helpful. Okay, as we work on this, hopefully I'll get better at presenting and I can get better at answering your questions. Remember, if you have a question, you want to get a hold of me that we can talk directly, we can use the Google Hangout, just let me know. So, remember, drive fast, take chances, do inappropriate things with people your own age. Be safe, guys. Miss ya.